Yeah, good evening. So, welcome to the last session. Just a second. Yeah. So, welcome to the last problem solving session of this course, that is Semiconductor Devices and Circuits, last regular week. So, this is week 12 of this course. And so, my name is Shomnath Bhattacharjee. I am currently pursuing my PhD from like the Department of Electrical Engineering, IIT Jodhpur. And I have been, for the past 4 years, I have been working on flexible and organic transistors for neuromorphic computing. So this is our last course. All the courses are already uploaded in YouTube, and you can also check the like the materials in the like I guess the link has been already shared. So this is the basic. This was the basic course structure. First, we have started with quantum mechanics, and then we have moved on to the solid state physics, different types of solids, and these kind of a things. And then we have learned about the density of states, Fermi function, doping, and these kinds of things. Then we have known about the charge transport, continuity equation, recombination generation of holes and electrons. Afterwards, we have moved to the junctions, different types of junctions, metal-metal junctions, metal semiconductor junctions, semiconductor junctions. Specifically, we have learned about like two different types of impurity-based semiconductor junctions, like PN junctions. Afterwards, we have moved to PNP junctions, or the BJT, the transistor structures. And then we have learned about the MOS caps, the capacitor structure, which have MOS structure. And then we have learned about the CV characteristics. We have learned about the MOSFETs and their usage in circuits, and various kind of a cases, like as a switch, as an amplifier, and these things. So finally, what we are gonna learn is the thin film transistors. So what a thin film transistor? Thin film transistor is actually a normal MOSFET, but as the film is thin, the semiconductor film is thin. That's why we are calling it as a thin film transistor. So this is our today's module. So first we already have learned the what are the large area electronics, what are flexible electronics, and why do we need it. Then we'll learn about the amorphous semiconductors, different types of amorphous silicon. So like up until now, what we have learned is that we have learned about silicon, germanium, and these kind of a thing. Those are the crystalline semiconductors. So what are the advantages, and there might be some trade-offs, obviously. So like what are these trade-offs, and like what more benefit do we get from utilizing this amorphous semiconductors? So just a second. So the first topic is, so first we need to know what is large area electronics. So whenever we need to make a very large area based transistor or a device, array of devices and those kind of things, the main problem arises because we need a large size of wafer. So a huge wafer is needed. So making it is obviously like fabrication is complex. Alongside, cost is very high. So how to tackle this? So if we need a very large area based device and a circuit or something like that, and there are multiples and multiples of transistor, what do we need to just solve this issue? So the complexity can be like minimized based on different architectures and structures, but the low cost, we need it to be a low cost, obviously, to like to be like very easily available in the consumer market, and that's why we need this large area electronics. So this is completely for the consumers, and the main thing of the main advantage you can say is that it can be used over a large area. How? So there are several kinds of things we can do. That is, one thing is printing. So we can print a transistor directly on top of a very selectively chosen substrate. We can roll it. So based on different kind of rollers, let's say this pencil is a roller, and if the transistor is fabricated at this stage, and if we roll it, based on that, the same contents will be printed over and over again. So this kind of a thing is called printing, like printing electronics and rollable electronics and these things. And so for this, we obviously know that a basic silicon wafer or these kind of a things won't work. So for this, we have generally what we use as a substrate is glass or plastics. So there are several different kinds of plastics like polyethylene terephthalate, that is the PET bottles. So we use PET bottles in our daily life and very easily, like for let's say mineral water or different kind of a cold drinks are stored in this kind of a PET bottles. So these PET bottles or PET plastic can be used as the substrate of these devices. Apart from that, a glass or like let's say a sapphire glass or a normal glass can be used for this, like clean like so these are the biological slides or those things can also be used as the substrate in these cases. And then the second advantage of this is low temperature processing. So why do we need a low temperature process? Because low temperature process also, like the first point is that it reduces the cost of making the devices. That is like one of the main thing that can like put your cost to a half, or let's say at one fourth of the normal cost it should have occurred or something like that. So low temperature process is necessary, but based on this low temperature process, the issue occurs of the semiconductor becomes amorphous in most of the cases. So these low temperature processes are necessary. And what are these low temperature processes? These can be spin coating or dip coating, these kind of a things. So this spin coating is when you are dropping a simple liquid on top of a spinning substrate, and the substrate spins, and based on that, the liquid is liquid is like rolled or kind of a like liquid is flowed over the surface, and there is a very smooth film, and based on that, the we are depositing each of the layers. Dip coating is very easy, so it's just dipping into an liquid or something of that kind. So these are the main two things, and the third one is obviously low cost fabrication. So large area electronics have main three things. That is the large area. It can be used over a large area. It can be processed in a very low temperature, and also the cost of fabrication is very low. That is why we'll use this large area electronics, because that in most of the cases, so we need for the basic consumer, we need to take the cost to a very low level, and that is why this is necessary. Now, so here what we have known about this is the amorphicity. So what is amorphous? Let's move to this. So what is amorphous semiconductor? Amorphous semiconductor is, up until now what we have learned is that we were working with a crystal semiconductor that has a very ordered structure. So, so that's why we were calling it as crystal semiconductors. But in this case, because of this low temperature processing and everything, what happens is that it becomes disordered. There can be a very small section of ordered, like it can be like this, but there can be like the large area, over the large area, what we can say, it is completely disordered. So this is called the amorphous semiconductor, and this is like happening mostly due to the low temperature processes and everything. So the first thing we need to know is that because of this amorphous semiconductor and usage of this amorphous semiconductor, we are moving towards something called the organic electronics. And why do we need the organic electronics? So it is completely environmental friendly, and we know that we are moving towards the circularity, that is the circular electronics, where we are using a device. We are not throwing it away because it will increase the amount of waste generated, and this waste generated is not like a normal waste. This is also, it is like in most of the cases industrial wastes, like in our everyday life we use electronic devices, and based on that it creates some waste that is called the electronic waste, and this is more harmful than total waste or total garbage like accumulation. And to and to reduce it, one of the major way is either we have to reuse it, somehow we have to reuse it, otherwise we have to completely dispose it. And there are several like heavy metals, and also there are several precious metals inside this electronic waste, so this is better to like reuse these kind of a things. So that's why we are moving towards a space where we in the future will be using organic electronics, or let's say biodegradable electronics, where we will use a device for a certain amount of time, and after the usage you will throw it away, and it won't harm the environment, and it won't disbalance the ecological and the human balance itself. So so these amorphous semiconductors can be of two types mostly. So they can be inorganic. In inorganic, the most used one is the amorphous silicon. And for the newer generation devices, for the recent devices that have been mostly in the R&D sectors, and recently it has started coming to the market as well. So these are the oxides, ZNO, IgZO, and these kind of a things, IZO. So these kind of a things are metal oxides. And for the newer generation devices, these have been used over the conventional silicon, germanium, and those kind of a things. But recently, what the work has been focused on is organics, and these organics can be like a single molecule one. So these can be rubberin and these kind of a structure. Apart from that, it can be a polymer. So small chain polymer, long chain polymer, different types of thing can be there. So these are like P3HT and these kind of a structure. So there can be something called pentacene derivatives. So these are organic semiconductors, and based on this, they like I'm not saying that they are harming they are not harming the environment, but they are like reducing the effect of this, and they can be reused as well. And so further we can we can search for for the material engineers. There is something called the biodegradable polymers, and based on that we can also make the devices. So the basic thing of this is that there are several trade-offs of this amorphous semiconductors with conventional crystal semiconductors. So what are they? So they are mainly, let's write the crystal one this side. The amorphous on this side. So most of all, the main thing for a transistor is the mobility, the field effect mobility, and gets the hit most. So for a conventional silicon transistor, the field effect mobility is in most of the cases greater than 10 to the power 3 centimeters square per volt second, whereas for an amorphous silicon it is in most of the cases it is less than 1. In some of the cases it can be up to 5 or something, but it in most like in the recent studies, or you can say it is not beyond 10 even. So there is at least 100 to 1000 times decrease in the field effect mobility. The the next thing is that the threshold voltage. So these devices in general starts at around less than 1 volt, whereas these devices have a huge range. So they have a range from 1 volt to let's say 20 volt, 30 volts. So this is the basic range. So most of the devices work under like let's say 1 volt, 2 volt, 3 volt, and they can work up to 20 volts even. And another thing to know is that the saturation current or the on current you can say. So in this case, the on current is in the range of milliamperes, which is a very high number, whereas for these they are in the microampere range, so at least 10 to the power 3 times lesser. But from this also we can consider that as the threshold voltage is lesser and the on current is lesser, so we can say these devices are also saving power as well. So apart from that, we can also say that applicability. So these can be used as a so they can make a complementary circuit such as CMOS and those things. But in most of the cases, this like amorphous silicons and the organic semiconductors and organic transistors, they are not able to do that. So in most of the cases, they either make a PTFT or an NTFT, although there are some there are also like some materials which show both the characteristics, but it is harder to make because like in case of organic I can say that in n type of transistors or n type of materials are not stable in air, and based on that we need a very high protection to maintain them, whereas mostly the p type of devices are stable in air as well. And also about this the threshold voltage is also um okay, so this was not threshold, so I would say this is the operating voltage, whereas like the threshold voltage. So threshold voltage is mostly stable. So like in these devices, mostly stable. So what does the mostly stable mean? So even if you change the temperature of the environment, so if your device is getting heated up and let's say they start malfunctioning and everything, but still the threshold voltage, the device will start around let's say 1 volt or something like that. But in most of the cases, these amorphous devices, it depends on the temperature. So the temperature variation has a high effect on this. So these are the basic trade-offs and these things. But although our mainly focus has been on this amorphous semiconductor devices, now to give you a recent perspective, I guess everyone has heard of the like previously it was the TFT screens. Nowadays, everyone knows that we use the OLED screen in our like smartwatches, smartphones, TVs, and everything. Everywhere there is a OLED screen, and recently everybody knows that AMOLED screen is like has been used for the past, let's say, 5 to 10 years or so. So this OLED means organic light emitting diodes. So this is a basic diet, but we have been for this they have used the organic materials to fabricate this. And why are we like shifting towards, like, let's say we are shifting from the conventional LEDs to like LCD. Previously it was LCD monitors and those things. Then we have moved towards the LED screens, then OLED screens, and then towards AMOLED screen. So we are reducing the power consumption through this. Along with that, we are getting a more saturated and a more accurate colors as well. So this AMOLED means active matrix OLED devices. So what does it actually mean? So in this case, let's say a basic OLED or a basic diode can be just a LED structure, but for an active matrix device, it have grids of some kind in rows and in columns, and each of the point is an OLED. So based on this, the TV screen or the phone screen can be look more brighter, and also it can give you perspective of the exact color we want to see. So this is the structure of active matrix OLED displays. And active matrix OLED displays are like also like it reduces the power consumption as well. So this has been the last week's class overall. And then I'll move to like some of the results from my research as well. So this is my research, and like I have fabricated these transistors. So this is the structure of my fabricated device. So this is on top of a ITO PET substrate, that is the flexible PET, which like the PET is derived from like bottles and etc. So what we can also do is that we can use we can cut out used bottles and try to what do I say, like try to straighten it, and devices can be fabricated on top of it as well. And for this case I have used all biodegradable materials. And this semiconducting material that is called the phthalo blue was extracted from toothpaste itself. So from toothpaste, so in sorry toothpaste itself. So in toothpaste we know like Colgate or these kind of a thing, there is a blue pigment in that, and that is completely edible as well and also biodegradable as well. So from toothpaste the semiconductor was what do I say, like the extracted. And then gelatin is from connective tissues of animals and like fishes and those kind of a thing. So this was extracted from that. So this is completely edible and this is completely biodegradable as well. Apart from this, apart from the metals and those things, everything is completely biodegradable. So this was my device, and you can see from here as well. So the current is in a range of like this. So the my saturation current was here, that is obviously less than 10 to the power minus 7 amperes, or obviously in the range lesser than like microampere. So you can completely see that these devices are working in a range of microamperes, whereas if they can work in a like let's say a milliampere range, it should have been a very good device, and what do I say, like a very good performing device as well. Although we can say that the so like it is not in a not in a like a root over structure. So what we can do is I can maybe do this, just a second. So as you can see, if you can just cut this, or I guess it should have been like this because there's a like a double structure or something like that. So based on that, you can see the, just a second, just let me do this. So based on this, we can see that the threshold voltage is very low as well. VTH is very low. although the mobility was like not that good enough, but these were the devices and they are completely biodegradable. So after using the device itself, you can just throw it away, and you can just like forget about it. It won't harm the environment. Although for these devices they have PET in it, and it was reused from bottles and everything. So apart from PET, you can also use some kind of a biodegradable substrate like paper. Like nowadays, people have been fabricating devices on paper, waste papers, and they can make the papers and fabricate devices on top of it. So these devices are completely biodegradable, and they are like they are green. So we are moving towards a greener electronics, and these devices reduce the power consumption as well. So this was it for the last week. So we'll move on to some problem solving sessions. And so like if anyone have any question, please let me know. So if there is no question, we'll move on to the problems. So like what I am gonna do for this week, as there is no specific problem for this, is that I'm gonna solve the problems from the assignment of week 4. So that was assignment 4. First try to solve this, and then we'll like discuss how to solve these things. So let's move on to this, I guess. So here, from here, what we can do is that first we'll start from below, I guess. So this is question number 9, that is a semiconductor has the following properties, where they have given dn as 25 centimeters square per second, dp as 10 centimeters square per second, tau and naught as 1 microseconds, tau p naught as zero point 0.1 microseconds. The semiconductor is a p-type with Na as 10 to the power 17 per centimeter cube, that is per cc, and held in equilibrium for t less than equals to 0. At t equals to 0, an external source is turned on, which produces excess carrier at the rate of 10 to the power 20 centimeter cube per second. Now at t equals to 2 microseconds, external source is turned off. What is the excess electron concentration? At t equals to 2 microseconds. So you have to solve this. now. So this was question number 9 of week 4. That was assignment 4. So think of it like how to solve this, and if any one of you have already solved it, let me know. Or or you can take at least 2 3 minutes and try to solve this. Otherwise, I'll give you the solution. And also not try to check out check out the answer and the options. Just try to solve this from your side, and then we'll check if the options are okay or not. Sorry, I was muted, I guess. So what I was saying that yeah, so what I was saying that try to solve this, don't look at the answer. Just try to solve this, and then we'll just match it with the solution they have already given. Don't directly check the options and try to fit the answer. So try to solve this directly. Take 2 3 minutes, 5 minutes, and then we'll discuss on it.
For semiconductor has the following properties: Dn is 25 centimeters square per second, dp is 10 centimeters square per second, tau no is 1 microsecond, tau po is 0.1 microsecond. This
Let me give you guys a hint. So first, to solve this, what we need to know is that, let's give you guys a hint. So first, to solve this, we need to write down the equation. So that is Tn del 2 del n divided by del x square plus mu n e del of n divided by del x plus gl minus del n divided by zno plus tau no, they have already given it. So del of del n by del t. Now from this, what we know is that we have two conditions here. Let me mark it down. So yeah, so there is a uniform generation going on. So based on, sorry, as uniform generation. So as there is a uniform generation, this term will move to 0. Now again, so apart from that, also we have no applied electric field at that time. Okay, so as there is no applied electric field, so that means E equals to 0. So this term will also become 0. So we'll have this equation only, GL minus del n tau n naught equals to del of del n del t. So you have to solve this equation first. At first, you have to solve this. Try to do this.
Sir, GL is the generation rate.
Yes.
Okay.
So, have you solved this like equation or not?
No, sir, not yet.
So, like, let me ask you guys. So, like, do I need to solve this like integration, or do I need to just put the integration down? So, if you need the total integration to be solved, I can also do that, or else I can just put the results and
Sir, please solve it.
okay, okay. So first, let me just turn this on. So first, what I'll do is that I'll just first give the solution of this thing, and I'll complete the question, and after that I'll complete the like integration then. Okay, so I'll do that.
Okay, sir.
Yeah, just a second. So this is the basic general equation, and by solving it, what we'll get is that del n e to the power of t by tau n naught equals to tau n naught gl e to the power of t by tau n naught minus tau n naught gl. Now, what we can write it as is del n is tau n naught gl 1 minus e to the power of minus t by tau n naught. We'll move to the next page, that is del n equals to, so what was the values? The values were tau n naught was 10 to the power minus 6, GL was 10 to the power 20 and in centimeter cube. So we don't need to change the limits or something. Now if we write this one into e to the power of, so it was 1 minus e to the power of t. So t is 2 microseconds. So 2 microseconds. So this is minus 2, right? This is minus 2 because it is 2 microsecond by 1 microsecond. So it should be minus 2. And we'll just use a calculator, just a second. So e to the power of minus, sorry, e to the power of e to the power of minus 2. It is 0.13533, and that would be minus of 1. So this is 10 to the power of 14 multiplied by 0.8646, something like this. And so I guess this is the answer, right? So if we want to write it, this is 8646 into 10 to the power of 14. So what was the answer there? The answer was 8.65. So this is same, right? 0.8 sorry, 0 point, or this is same. So we'll write this 8.65 into 10 to the power of 13 per cc. Okay, so this was the answer. So now I'll complete the integration. So let's move on to the next. So for this, the integration was what? Sorry, gl minus del n by tn equals to del of del n by del t. So this was the basic equation what we had to like solve before. Now to solve this, like we have to rewrite the equation, right? So how to solve this? So this is del t of del n plus del del n of tau n naught equals to GL. So like we can write it as this as well, right? So this can be written as del. It is not visible. Let's change to color yellow, let's say. So this looks very similar to del y del t plus y multiplied by 1 by t naught. Let's write it as, sorry, let's write it as p of y equals to q. So the form is very similar to this, right? And so based on this, we have to use the integrating factor equations. And so how to do that? And also we can say that here p is nothing but t n naught minus 1. Now we'll just use the integrating like equation. So first we need to find out what is integration of p dt. So that is 1 by tau naught. So this is 1 by tau and naught, because this is a constant value del t, that is t by tau and naught. So this is our factor we need to know. Now we need to find the integrating factor. So how to find out the integrating factor? We just have to put this. So we know our integrating factor is this. How to delete this? Okay, delete it. Okay. So this is our integrating factor. This is our integrating factor, and we'll just use it to like write down the equation. So the basic thing to solve this equation is, oh, shoot. Okay. So the basic thing to solve this equation is, so let me just write it down here. P equals to P was tau n naught whole to the power half, and Q is GL. Now, so how to write the equation? This is IF multiplied by Y equals to integration of IF multiplied by Q multiplied by dx plus C. So this is the basic equation of a integrating factor equation. So how to write it down? So IF is y into e to the power t by tau naught, and we have written exactly that here. You can see del n. So okay, let me do one thing. Let me just remove the y for now, because y we know that it was del n. So let me write it down here directly. So previously what we had is that del n e to the power of t by tau naught. Then the integration will be mm, e to the power t by tau and naught gl dx. And now dx was dt, right? So this will be dt. Now we have to integrate here, because there is e to the power t by tau and naught is there plus c, and we have to find out what is c as well. So this is del n e to the power t by tau and naught, and it would be gl multiplied by e to the power t by tau and naught multiplied by, so we have e to the power t by tau and naught and t by tau and naught. So this will be tau and naught. So 1 by tau and naught t squared by 2. So this will be tau and naught plus c, right? And now to find out c, we need to put t equals to 0. Let's say t equals to 0. Then the first term would be 0 equals to, so also 0, right? This is 0 and this term is 0. Okay, so we also have to put x equals to 0 as well. Let's put it as this. So this will be this, and this would be tau n naught gl. This term is 1. So this will be plus c. So c will be minus tau and not GL. Now, if we write down the equation here by putting this value, this will be del n e to the power t by tau and naught plus GL e to the power t by tau and naught multiplied by tau and naught equals to minus tau and naught into GL. I guess this was it, right? Tau and naught GL, tau and naught. So I have just written them in opposite factor. So this is we how we need to solve this equation. This is through the equation called the integrating factor equation. So this is integrating factor process to solve the equation. Is it okay? Or are there any like calculation mistakes or something? Because otherwise I have to check it. I guess this is fine. Let's move on to the next one. So the next problem was what? Problem number 8 was there. A silicon wafer is maintained at T equals to 300 Kelvin with 10 to the power 15 per cc donor atoms. Light irradiating the wafer leads to a steady state photo-generated density of electron hole equal to 10 to the power 19 per cc. Assume that the wafer is very thin when compared to the absorption depth. So that means throughout the wafer, the light is getting absorbed. For the light, so that, yes, so they have also written that so that the free carriers are uniformly distributed throughout its volume. What is the position of the quasi Fermi level for holes below the intrinsic Fermi level? So we need to find the distance between them, and we need to find it out in EV as well. So try to do this. Take 5 minutes and try to solve this as well. So if anyone was able to solve this during the assignments, they can also like tell me the answer as well, and the process how to solve this as well. If not, then try to solve this right now. I'm just writing down the values. What like we have from this equation is ND, we know that is 10 to the power 15 per cc. We know del N equals to del P equals to 10 to the power of 19 centimeter like per cc as well. And we also have now total hole concentration is P, that is P naught plus del P, so the generated one than the first one. And also they have given is, so Ni, now Ni is not given in the equation, so you have to choose what to put in Ni. Ni can either be 10 to the power 10 or 1.5 into 10 to the power 10, so you can put any of that. And per cc in both the cases. And apart from that, they have given T equals to 300 Kelvin. So the value of KT we know from that, that is 0.0259, or you can also put 0.026 in EV. I don't think anything more is there. So just try to put these values in the equations. Let's try to do one thing. Um, let's try to do it for two cases as well. So for case 1 and case 2, as they have not given Ni in the equation, so for the first time put 10 to the power 10, and for the second case put 1.5 into 10 to the power 10. then just give the equation. Just put the values then. So we know that this difference is nothing but EF intrinsic minus EF this KT ln P by Ni. So it will be here as well EFI minus EFH equals to KT ln P by Ni. Just put two different Ni values for each of the cases and try to find out what is the values for each of the cases as well. And let me know the answer as well. Um, for which case? It is 0.62 for the case 1 or case 2? We had the range is 0.3 to 0.6. Okay, so this is for case 2 1.5. If we put 1.5, the value is this. Why? This is 0.0259 ln of P by del P, right? So that is 10 to the power of 19. For which case that is 0.53. 1.5 into 10 to the power of 10. Let me just put the values first. So 10 to the power of 19 divided by 1.5 divided by 10 to the power of 10. For case 2, this is 0.53, okay. And we need to find out ln of this is 20.3. So this is nothing but 0.0259 multiplied by 20.3178. So if I multiply with 0.0259, it is 0.526. Yes. So we can write it as 0.53 or we can leave it as this as well. So if we just want to put it in this, we can write it as this as well. So the answer that was given in the question was 0.6 to 0.3. So it is already we have got this value. So let's right now put it in this. That is ln of 10 to the power of 19 by 10 to the power of 10. So this is just directly straightforward. So we need to find out ln of 10 to the power of 9. So that is 0.0259 multiplied by 20.7232. So if we multiply 0.0259, that comes out to be 0.5367. So it is 0.54. So there are two possible answers as well, but as they have given 0.3 to 0.6, both the answers are correct obviously, as there is no written NI value. But I don't know why the range was 0.3 to 0.6. There might be some reason it may be coming out to be 0.3 or something. Hmm, let me think. So anyways, the generated electron or hole both is 10 to the power 19, and adding something with that value is normally like, so what I am talking about is that this is like this. This is essentially del P because del P is 10 to the power 19 and there is a 9 order difference between both the terms. So anyways, P is nothing but equals to del P. So these are the two values I am getting. I'm not sure why there was zero point 0.3 to zero point 0.6 range because everything is coming out to be zero point 0.5 to zero point 0.6 range in that range. Okay, so leave it. Let's move on to the next one. So after 8, where is it? Yes, so this is, so we'll be working on question number 5. Let's say, oh, sorry, my camera is not turned on. Okay, let's say there is a machine that can set the mobility of dominant charge carriers at will without other parameters, without altering other parameters. So we have a machine that is able to change the mobility, but it is not affecting the other parameters. Now, okay, so if you have understood the flow of the concept, you will quickly realize that I can build a filter of desired cutoff, right? So now what we have to do is, so say I decided to build a low pass filter. Say I have decided to build a LPF, that is low pass filter, with a cutoff frequency of 10 kilohertz. So the cutoff frequency is 10 kilohertz, but due to some error, I end up with a filter cutoff frequency of 12.5 kilohertz. So our mobility is not dependent upon any of the other parameters. So we are changing the mobility to change the cutoff of the filter. Now a filter that was desired to be having a cutoff of 10 kilohertz now have 12.5 kilohertz. Now what the question saying is, upon characterizing the semiconductor, the mobility comes out to be value set on the machine. So there is no issue with the mobility. This means there was an error in fabrication at doping site. Now find the ratio desired doping concentration to the doping concentration present in the semiconductor sample. In the semiconductor sample. Yeah, what was the question? I don't know. So FC 10 kilohertz. Yeah, so the cutoff frequency, estimated cutoff frequency was 10 kilohertz, but we have got 12.5 kilohertz. Now we need to find out the ratio of doping concentration in these two devices. So just one of you can just explain the question. I guess I'll give the answer directly, but just explain the question if you have got the question or not. Is the question clear? So we have a device which have a mobility that can be set on the machine itself. Now what they have done is that they have prepared a low pass filter, and it should have a cutout frequency that was F1 in the question itself. So they have mentioned it as F1, which is 10 kilohertz, but mistakenly it has become F2, that is 12.5 kilohertz. Now we have to find out the concentration concentration ratio of these two things, and there was a doping error. So just I'll just give the answer itself. Now we know
Sir,
that
both frequencies are divide by 12.5.
both frequency means, um can you repeat that again? I didn't get that.
Sir, in question, find the ratio of desired doping. Come to the doping concentration present in the semiconductor sample.
Yeah.
Uh, okay.
So
I
this is a bit hard one actually. So first, the main thing we need to know is that the cutoff frequency, how to get the cutoff frequency of a LPF. So there's the basic problem was there. So I'm solving it. So now LPF cutoff frequency is 1 by 2 pi RC. So the value of LPF cutoff frequency is 1 by 2 pi RC, and the resistance or impedance, you can say, of the semiconductor is given by L by A multiplied by mu n mu p multiplied by the charge. So from here what we know is that there was fabrication of doping result. So now the question arrives. Let's say we don't know what kind of a doping they are talking about. So let's say it is a n type doping. So let's say n is much greater than p, and the doping concentration is nd. Okay, let's have it like this. So what will happen is that we'll just put the values. Let's move on to the next page, I guess. So the resistance value, if it's r, it is nothing but L divided by, so we can remove the other part, so aq into n mu n, right? So we are removing the p part because n is much greater than p. We are just assuming that it is an n type one because they haven't mentioned. So we can also do it using the p type one as well. Now the doping concentration is nd, so we can also write it as aq mu n nd. Now they have also mentioned that we can change. So for the cutoff frequency, f is 1 by 2 pi rc. So r is L by aq mu, sorry, mu n nd into c. Now if we are writing this is aq mu n nd divided by 2 pi lc, right? Yeah, 2 pi lc is there. Now what they have got is f2 by f1. F2 was there. So let's not do this. So F1 by F2, let's do it like this and then we'll move it afterwards. So AQ is remaining the same because the area and the charge is all the same. Mu n is also same. ND divided by 2 pi L, sorry, 2 pi LC. So they are changing this value only. So let's put it as ND1, AQ mu n, ND2 by 2 pi LC. Now if we just put the values here, so this would be ND1 by ND2 and this is 10 by 12.5 or this is 0.8, right? 12.5, yeah, 0.8. So the value is 0.8. What was the answer there? The answer was zero point 0.8. So like basically you were saying that you are just getting the ratio of these two values. But mainly the reason is that we are moving towards the LPF cutoff frequency. So we have to put 1 by 2 pi RC and then we have to get the values. And you have also, we need to also remember that the cutoff frequency equation is 1 by 2 pi RC as well. And the resistance equation as well.
Sir, but in this type of question, always we assume always n is greater than p,
No, not necessarily.
and if p is greater than n, then
Then the same thing will happen, right? Just a
okay,
second.
okay,
So let's say, if let's say P was greater than N, so Na would have been Na, right? This is the basic difference. So the equation would have been L by A P mu P Q. And now here, sorry, A P mu P Q, and this P value would have been Na. That's it. Everything would have remained the same
okay, sir, okay, okay.
because we don't know what kind of a doping is there. So like if because they have just written that desired doping concentration, so it can be a n-type doping or p-type doping. Obviously it can't be both, right? So one term is greater than other one, so we are just assuming this. Let me write it down. So assuming there is a n-type doping happening, because they haven't mentioned that this is the n-type semiconductor or a p-type semiconductor. If it has been given there, so we would have assumed that only. Even if it is a p-type semiconductor, it would be look like this, and everything there would be p mu p. And in both of the desired case and also the uh, what do I say, like in f1 case and f2 case, in both the cases everything would have just crossed out, so there would have been na1 by na2 and the value would have been same as well. Okay, so let's move on to the next one. So after 5 there is, we can't do the fourth one, so let's move on to the third one and then we'll move back to fourth one. So the third one, let's say I have a intrinsic semiconductor. Now I dope this with group 5 impurities at concentration of 10 to the power 20 per cc and obtained a doped semiconductor such that the conduction is completely dominated by electrons. I cut out a sample of cubical structure of each dimension. So this is the sample dimensions itself, 1 centimeter. So we have a 1 cc volume cube from the dope semiconductor, and tell you that the resistance. So this is also another resistance problem. So the equation is already given there. Obtained when measured across opposite faces is zero point 0.1 milliohm. The mobility of electrons, that is we need to find out then mu n in this semiconductor, is question mark, and they have also given the value of q, that is 1.6 into 10 to the power minus 19. This is also another easy one. So take 2-3 minutes and try to solve this. This is the easy one. And we also have gotten the value of r as well recently. So in the previous question we have used this r, and but in this case as well you have to use p mu p plus n mu n. But another thing to note is that somewhere they have, yes, so they have already told that it is completely dominated by e. So that means as it is completely dominated, then n much greater than p, so they are already given this thing. Try to solve this. So has anyone got the answer? So I'll provide the answer then. So so they have already told, like in the question it is already written group 5 impurity, so that means that the dopant is Nd, okay, as it is group 5. Now we also know this is it because this is already dominated by E greater than P. So what we'll do here is that we have to just find out this. So they have already given R equals to 0.1 milliohms, right? So that is 0.1 milliohm, and we just have to find out what is the value of these values, right? So from this we already know that it is L by EQ N mu N P mu P. So we have already used this formula previously and we'll just use it again. So now similarly in the previous case, as N was much greater than P, so R would be L by AQ in mu N. So this is exactly similar as the previous case. Now what we'll do is that what are the values we have got, and this is 0.1 milliohm or 10 to the power minus 4 ohms. Okay, now we know the value of L here because all the sides are 1 centimeter. We have the value of A, we have the value of Q, we have the value of what are there. So we need to find the mobility. So it is directly, we can write it like this. Mu n is, let's write it down like this. 1 centimeter divided by 1 centimeter square multiplied by 1.6 into 10 to the power minus 19 multiplied by 10 to the power 20. So this is nothing but 10 to the power minus 1. So the value would be 1 by 1.6, 1 by 16. So the value is 1 by 16, that is 1 by 16. So the value would be 0.0625. The mobility is 0.0625. Let me check what is the answer. Where is it? Okay, now there's a problem, I guess. I have miscalculated somewhere. The value shows to be 620 to 630. Okay, so let me recheck it again. So this is in centimeter, this is in centimeter. Q is in, okay, mobility is centimeter per centimeter. I'm not sure where is the problem. 1 by 16, let me. So what have, like you guys have got the value? I may have mistaken somewhere because from the question it looks like the answer should be like this. So I have 10 to the power. Oh, okay. Sorry. I forgot to just multiply this term. So it should be this. Then it should be 10 to the power 4, right? And this is 10 to the power 4, or this is 625. So I just forgot to multiply this milliohm term. Is it okay? I guess it's okay. So let's move on to question number 4. That was the extended portion of this question. So let's say the semiconductor obtained after doping. Let's say the semiconductor obtained after doping is put to use in a system operating at 450 Kelvin. Find the value of Dn. Value of Dn and in centimeter square per Siemens. Okay. So it is also a straightforward thing. Let me just give you the answer then, and then we'll move to the next question itself. So first we need to find out what is KT, right? So for this, KT value will be, what is the value of K? Just a second, just multiply it. KT is 0.026, so 0.026, so it would be multiplied by 450 divided by 300, so it is 0.039 on an average at 450 Kelvin. Now we just have to put the value. So Dn is nothing but Kt by Q multiplied by mu n. Now we have got the value of mu n as 625. So this is 625 multiplied by 0.039 divided by Q is 1.6 into 10 to the power minus 19. We'll just put the values. This is 625 multiplied by 0.039 divided by 1.6. So this is nothing but 185.86 multiplied by 10 to the power of 19. Let's write it down like this. So what was the answer? The answer was 13.5 to 15.5. Why is it like that? Hmm, 13.5 to 15.5. No, wait a second. So it was, how much was it? So they have asked about the coefficient. Now, if the coefficient is dn, so in centimeter square per Siemens, that is 10 to the power 20. So that would have been 18.5. Still, it's larger than that. Okay, so they have given the value of kT. So kT at 0.025 EV when 300 Kelvin. So I guess we have to just remove this value. This is not how we'll do this then. Then kT at 450 Kelvin would have been 0.025 multiplied by 450 by 300. So the value would be different. 0.025 into 450 divided by 300. So the value would have been 0.0375. Sorry, so I didn't check the question. So in the question itself, they have also mentioned that KT at 300 Kelvin is 0.025. So we can't assume it as 0.026. So the value would be like this, and based on this, this value would be changed 375. So multiplied by 625 divided by 1.6. So this is 14.6484 multiplied by 10 to the power of 19. So this is okay. So the value they have given is 13.5 to 15.5, and it is inside that, so we can write it as 14.6 into 10 to the power of 19, which is in the range of 13.5 to 15.5. So the main issue is that if we have used this value, it would have it would have been outside the range, that is 13.5 to 15.5, because it was coming out as 18 point something, I guess. So we can't use that value. Okay, so let's move on to the next question. That was this, right?
So please explain the value of KT
Um, was
0.02.
it was it not visible at that time? Okay. I'll go through it again. So what we have done is that, like previously I was doing this KT as 0.039. So based on the value of Boltzmann constant and temperature, I have calculated this, and based on that, this value was coming as 18 point something, and that was wrong because in the answer it was given as 13.5 to 15.5. So I didn't know what was the problem there. Then I found out that in the question itself they have given the value of KT as 0.025. And just a second.
Okay, sir. Okay.
Yeah,
Yes,
so
got it. Got it.
from here what I have done is that I have multiplied it with 450 and divided by 300. So now it is 0.0375, and after multiplying it, it is coming out as 14.6, so which is inside the range 13.5 to 15.5. Previously, if like as I was considering this value, and based on that it was coming out as 18 point something, and that is beyond the range, so I was confused why it was not matching the answers. Okay, so let's move on to question number 2 then. Question number 2, the question is: a semiconductor having an intrinsic carrier concentration of 10 to the power of 10 per cc is doped with 10 to the power of 15 per cc donor. After doping, the Fermi level is located at EF naught. EF naught. So they are just mentioning the um, after doping, right? So the Fermi level is notated as EF naught. Now the doped semiconductor is irradiated with 10 to the power 20 photons per second, such that each photon impinging on the semiconductor leads to the generation. So that means it is not the not the amount of photon, but the amount of electron generated and the hole generated. So generation of one electron hole pair. So del E, that is del N, and del P is 10 to the power 20 here. That is, they are saying during illumination, during illumination, the Fermi levels for holes is located at EFP. So now it has shifted to EFP itself. Given thermal voltage is exactly at 25 millivolts, the minority carrier lifetime of holes is, so they have also given tau p, that is 10 to the power of minus 6 seconds, that is 1 µs, and the value of EF naught. So that is the normal Fermi level minus when the Fermi level is shifted based on the irradiation. So based on del P and del N. So what is the shift in EV is closest to? So they are telling to match the values. Try to solve this. It is like moderately hard, not that much hard, but like it is still hard. So take 2-3 minutes and try to solve this. Maybe I'll give you a little hint. So if we are just drawing the Fermi level, so this is okay. So this is our basic band structure. Now this is the conduction band and this is the valence band anyways. So first, no, let me remove this. So this level is our intrinsic Fermi level, that is EI. Now what they have done is that they have been it has been doped with intrinsic Fermi level is located. The semiconductor is related to 10 to the power photon. A semiconductor having an intrinsic concentration of 10 to the power 10. So they are saying that it is EFP. So let's have it like this. So the Fermi level has shifted from EI to EF. EF, what was that? EF naught. Okay, so this has been shifted to EF naught. Now what they are saying that the doped semiconductor is irradiated with photons such as the it increases the electron and hole pair. So based on that, what happens is that now based on this photon, it will be shifted like this. So this is called EFP. Now we have to find the difference between these two. So we have formulas to find this out. That is, what is the difference between the intrinsic to the extrinsic one. And then we have also the formula of this from intrinsic to how to change it to EFP, that is the based on the thermal generation or the photon generation, what is the new one. So we just have to like get these two values and then sum those things. And I'm for it to be like I am also writing these things. So NI they have given us 10 to the power 10 per cc, sorry, per cc. They have given ND as 10 to the power 15 per cc. Apart from that, is there anything more? So it is enough to just calculate the value of this. So that is from I to FO. Let's write it like this. So for this case, we know EF naught minus EI is nothing but KT ln of ND by NI. So it is very straightforward, 0.026 multiplied by ln of 10 to the power 5. We can directly get this value. So the value would be ln of 10 to the power of 5. So this is 11.5. Let's say it is 11.5. The value is 0.026. The value is 0.2993, or we can write it as zero point 0.3 as well. Now for this, so we now have the first value. So this is already done. This is the second one. So for that, what we need to do is we need to find out the value of G. So let's move on to the next page. For that, we know that P is Ni square, sorry, Ni square by Nd, that is 10 to the power 5 per cc. Now we need to find out generation, that is del P by tau P, and del P we already know. So from this, we also can write that del P is G into tau P, and they have given that the generation was 10 to the power 20, and this is 1 microsecond, so it was already given there. And based on that, we can write 10 to the power 14 is del P, and P is 10 to the power 5. So from this, we can also write that del P is much, much greater than P. Okay. Now from this, we can write that now, like the P effective value is del P plus P, or we can write it as del P, or we can write it as 10 to the power 14 itself per cc, per cc. So while putting the values for this, so we know that the value is EI minus EFP is KT ln of in A by in I, or we can write it 0.026 ln of in A is 10 to the power of 14, in I was 10 to the power of 10, so this is 10 to the power of 4. Let me just put that in the equation. So ln 10 to the power of 4 is 0.026 multiplied by 9.21, 0.026. So the value is nearly 0.2394. Now, so we have the difference between the first one, that is from the intrinsic to that, and from this to that. So we'll just so this is ei plus ei minus, so we'll just add both the values, right? So we need to find out this ef naught minus efp, so we'll just add both the values, that is 0.299 plus 0.239. So the values would be 0.299 plus 0.239, that is 538, 0.538 in EV. So what was the answer? Okay, so the answer was from 4 to 6, so this is the answer. The answer is correct. So based on the point assumptions and like decimal points after decimal point, so based on that, the answer may change from point 4 to point 6, but for my case it is 0.538. Now let's move on to the last question of today. So a p-type semiconductor has 10 to the power of 10 per cc intrinsic carrier concentration. So that means we have the value of Ni as 10 to the power 10 and 2 into 10 to the power of 16 per cc dopant concentration. So if the and also they have mentioned this is a p-type one. So if the electron and hole mobilities are 10 to the power 3 centimeter square per volt second. So electron hole mobility, that is mu n and mu p, both are same. And no, sorry, I mistaken. So they have mentioned that electron mobility is 10 to the power 3, whereas the hole mobility is 5 into 10 to the power 2. Now we need to find out the resistivity, that is rho, in ohm centimeter. They have also given the value of Q as 1.6 into 10 to the power of 19. So it is a very easy one also. Maybe I'll just solve it because we don't have that much time remaining. So, so what they have given is Ni as 10 to the power of 10 per cc. They have given mu n as 10 to the power of 3 centimeter square per volt second and mu p as 5 into 10 to the power of 2 centimeter square per volt second. And we need to find out the value of rho. So that is it. We know rho has a value of this Q multiplied by P mu P plus N mu N. Now we know the value of mu N, we know the value of mu P, we know the value of Ni, and we know, oh, okay, so we know the value of Na as well, that is 2 into 10 to the power of 16 per cc. So from this, we have anything more or not? From this, I don't think we have anything more. So for this case, we can say that P is much greater than N. So based on that, rho can be written as 1 by Q P mu P. And based on that, what we can write is 1.6 into 10 to the power minus of 19 multiplied by P. So the value of P is 2 into 10 to the power of 16 multiplied by mu P. Mu P was 5 into 10 to the power of 2. So, and this would come in ohm centimeter anyways. So let's just put the values in here. So the values are 1.6 into 10 to the power of minus, sorry, 10 to the power of minus 19 multiplied by 2 multiplied by 10 to the power of 16 multiplied by, sorry, 10 to the power of 16 multiplied by 5 multiplied with 10 square. So the value is 1.6. So this is 1 divided by 1.6, and that is 1 divided by 1.6 is, sorry, just 1.6 is 0.625 ohm centimeter. Let's check the answers. So the answer was 0.62 to 63. So we have got the answer itself. So this is 0.625 ohm centimeter. I guess this is it. Yeah. Let me write it down. So anyone have any question on this like problems what we have solved this like solved today? So as per the request, I have gone through the assignment 4 and tried to solve all the numerical problems. Others were like basic MCQ type of questions. which can be found out from the lectures and also from Google itself. So I've tried to go through the numerical problems in assignment 4, that is week 4. So anyone have any questions, or else we'll end the session today. Yes.
Yes, thank you, sir. Thank you so much.
Yeah, no worries. If you have any more queries regarding the assignment itself, let me know, and then I may take an extra class or I'll send the solution. Okay?
Okay, sir. Okay.
Yeah.
Thank you. Thank you, sir.
Yeah, no worries. Thank you. Thank you for attending.